It's much lighter than anything you would make out of steel. It's very light to transport.
So for the construction industry, this would look and feel and work exactly like normal carbon fibre.
Absolutely. It operates the same way. It is just lighter and it has the same strengths as anything you would make out of concrete. And it is carbon negative.
The world's population is expected to stabilise in the next 60 years before decreasing. In the meantime, it continues to grow. To accommodate that growth, we need more construction. But that means more emissions.
The building industry and construction materials such as classical Portland cement are responsible for about 7% of the anthropogenic CO2 emissions worldwide. It's very hard to reverse because during the process of burning chalkstone, you emit CO2. This is something you cannot avoid, and you do this at 1,400 degrees. If you use fossil fuels to emit this energy, you become a major carbon emitter. To reverse this, we need to come up with innovations that lock away carbon and not emit it anymore.
There's a movement growing to develop alternatives, incorporating biomaterials found naturally into buildings. At the Technical University of Munich in Germany, they're developing a literally green alternative to one of the most in-demand building materials.
This is our algae collection. We're focusing on saltwater algae. The name of this creature is Nanochloropsis salina. It actually comes from a marine environment, and it has the property to actually generate up to 50% and more of oils in its biomass when you stress it a little. And one of those properties is that after the growth, so this is actually in the growth phase right now, you deprive it of nutrients. They stop growing, get stressed, and they accumulate oils inside their cell as a stress response to save carbon. And at that point, we actually harvest them and use them for making carbon fibers.
Algae are emerging as a versatile and sustainable resource in the development of carbon fibre, one of the most commonly used building materials.
What is algae?
You can describe algae as a very primitive plant. They're unicellular organisms. They live in the water column or attached to a substrate. Nanochloropsis is very robust in terms of changes to the environment. So changes in salinity, changes in temperature, and also changes in nutrient availability are fairly well tolerated.
Here at Professor Thomas Brooks' labs, they're cultivating Nanochloropsis for research. But over in Otterbrunn, they are creating up to 500 litres of it, not just for carbon fibre, but also biofuel.
What makes algae so special?
It grows very fast. For example, it's growing 10 times faster than any terrestrial plant. It has 14 times more oil yield, and it doesn't use any fresh water or agricultural land. So the cultivation of this organism is independent of agricultural activity.
So what's the next step for this algae?
So that's the next stage. Of course, the small cultures that you saw in the chamber needs to be enlarged.
Right.
And the next step is to actually put them in these Erlenmeyer flasks. In this cultivation chamber, we are optimizing light input, input of CO2, and the cultivation duration. So the time it takes till we start the next stage of accumulating oils. Yeah? It's basically a step up in volume in the process development.
And how long will this take?
So this is usually a week or two, depending on the algae that we cultivate. But for nanocrops, Salina, because it's a very fast grower,
Yeah.
about 7 to 8 days is completely sufficient. So what we have here is what we call a controlled photobioreactor, a flat panel reactor where you very definitively can dose the lighting into the culture. How much photons hit the culture at any one time, because too little as much as too much light actually damage cell growth and inhibit maximum biomass efficiency. So here we can actually dose this very efficiently.
So you're testing how much light is the right amount?
Correct.
Because the algae requires not only light but constant CO2 to grow, it means this process is not only carbon neutral but carbon negative.
The next step is harvesting them, and what you end up with is this kind of algae paste.
Wow, it's really thick.
Yeah, it's very thick, but it still contains water.
Right.
And that water, we still need to get rid of it. And what you have here then is algae powder, which is then basically the same what you buy in a health store or spirulina that you put in your food, but it's now the raw material to produce our carbon neutral carbon fiber.
The team take the algal biomass and process it to produce yeast oil, which is treated to produce glycerin, which is then converted into polyacrylonitrile, the basic material in the manufacture of carbon fibre.
This is algae-based carbon fiber, and every carbon atom that is in this fiber was formerly CO2. And with the process that we're currently practicing, we're not only becoming carbon neutral, we're becoming carbon negative, because anything that is adopted by the algae, even with the energy input of light, is saving carbon from the atmosphere.
Incredible.
And it is locked away,
Yeah.
basically, in this form of the carbon fiber.
So what can this then be used for?
So the first step usually is to take the carbon fiber and make a textile type material, and this is what you see here.
Okay.
Yeah, so it's basically carbon fiber as a mesh. It's woven, classical textile
Yeah.
technology. And what you can do then in the building sector is you make it into more rigid components by cutting this and mixing it with algae oil. It's
Wow.
also a technology
That's
that
great.
we develop. So this mesh is then put into concrete and substitutes for steel. Steel, as you know, is very energy intensive. We reverse that cycle and it can't rust. It's as strong as steel, but it's more flexible, so you actually need less concrete for the same stiffness and load-bearing performance as you would with steel. That's a two whammy, because you have less impact on the material use. That also reduces your carbon footprint.
In an industry that desperately needs solutions, green carbon fibre is a viable material in many building structures like walls and frames.
So, Gabi, what we have here is one of our demonstrators. Yeah, it's one of the demonstration activities that we have for carbon fiber stone. It's much lighter than anything you would make out of steel. It's a drone landing pad. It's very light to transport. Yeah, in contrast to anything equivalent you would make out of steel, and it is carbon negative.
So for the construction industry, this would look and feel and work exactly like normal carbon fibre.
Absolutely. It operates the same way. It is just lighter, and it has the same strengths as anything you would make out of concrete or steel.
And it's here, just outside of Munich in Dachau, where a team at Technical Technologies developed this novel composite material. Kolja Kuz, once an electrical engineer, developed carbon fibre stone using a blend of granite and Thomas's unique algae-based carbon fibre.
This is the new generation of house walls that we utilize to decarbonize air.
So what makes this wall so special?
At the moment, this is the best wall on planet Earth. It's 2 times lighter, it needs 2 times less energy, it comes at 2 times less CO2 emissions today and will become highly carbon negative in the future, to the same amount that walls from today are carbon emitting. This is the future. And we need this because we need to decarbonize our atmosphere. So we need to take out CO2 from atmosphere and not only use waste gases from the industry. We need to become carbon negative to make our climate goals.
So how have you made this wall?
Between 2 stone plates reinforced with carbon fibers, we have biochar as insulation material. Wow. It's very lightweight. It has incredible insulation properties, and it's highly carbon negative, in addition to the negativity of the algae carbon fiber that we are utilizing here.
So this is the insulation that's in there?
Exactly. There's a lot of insulation material in here because the 2 stone plates are only 2 centimeters wide. So all the rest is insulation room, so to say.
So in a normal wall in a house, what would the insulation be? What would be the sort of the downsides of it?
This is made from plastics today, which is glued on top of a thick wall of concrete, steel reinforced concrete, that is highly carbon intensive. But what we do is highly carbon negative. 1 square meter of this wall will absorb 59 kilograms of CO2 from ambient air. Wow. Through our 3 methodologies.
By using biochar, or biological charcoal, the carbon fibre stone is only adding to its green credentials. My colleague Rhea El-Salahi visited a carbon removal facility in Wales that's producing biochar from algae, currently for agricultural use.
So this is a tub of microalgal-based biochar. It has an increased surface area, which helps with the nutrient dispersion and where it goes on the agricultural land, but it's also a more stable form of carbon. So charcoal would decay a bit quicker than biochar does. So we can pretty much guarantee that the carbon that we have removed will stay stored and out of the atmosphere for at least 1,000 years.
What happens after that 1,000 years?
So there is a lot of evidence to suggest that it might actually stay for 10,000 years plus, but the agricultural benefits of it will then disappear after 1,000 years.
Over a year, this bioreactor array can produce around 64 tonnes of dried algae, which has removed 115 tonnes of carbon dioxide from the atmosphere. Once all the water is driven off, they end up with 40 tonnes of biochar. Where does this end up? Where does it go?
All of our biochar is currently used in an agricultural setting here in Wales. Once it's put on the land, it acts as a really good soil additive, which means it both adds nutrients to the soil in which it's added, and it also adds structure to the land that it's put on.
Here in Dachau, it's the biochar providing the insulation in the composite material. Working together with the compression-resistant stone slabs and a tension-resistant layer of those carbon fibres to produce a material that in lab tests was shown to exceed the performance of steel and steel-reinforced concrete. But it also has one unexpected quality.
This is a waste sample from cutting with the water jet. Here you can see the fine layers of the carbon fiber on the surface. This is only 0.3 millimeter thin, and all the rest is stone. And now you can see that the stone is flexible once it's stabilized with the carbon fiber. And this makes it very robust and even flexible in situations of earthquakes.
So that could save lives.
Life-saving, and its longevity is hundreds of years.
So it really is a super material.
You created a new expression. It could become the super material of the future, yes.
It may not seem like something to get excited about, but innovations like this are vital to change the construction industry and reduce its enormous carbon footprint. In fact, if 250,000 homes were built with carbon fibre stone in Germany every year, 10 million tonnes of dangerous CO2 emissions could be bound and stored for the long term. For their work, Collier, Thomas and their teams won a recent Innovation Award. But to replace cement and steel at a large scale requires huge scaling up. That takes time and money. But algae's low cost, fast growth means its production capacity is much greater than any other natural resource or source of energy. As well as being one of the world's largest emitters of carbon dioxide, the construction industry is also one of the main contributors of waste to landfill in the world. Innovators are racing for solutions.
But could the solution lie not in finding new, more green materials, but reusing old materials?
We've come to East Lothian in Scotland to see a green alternative to one of the most environmentally damaging building materials.
So this is Kenoteq's first product, the K-brick. Looks, acts and feels like a normal brick, but this is not just a normal brick.
Sam Chapman, together with his co-founder Gabrielle Lawrence, saw an opportunity to stop old demolition and construction material going to waste.
This is an ultra-low carbon building brick made from recycled demolition and construction waste. Over 90% of the material used to make this brick is from recycling.
Why do we need a brick like this?
The construction industry is one of the largest contributors to the waste industry and the waste in the system, both in the UK and in developed countries. But also it's the largest emitter of carbon emissions. So combine those two things, the industry needs products like this to make a real sustainable improvement to the way that we build today. After the initial lab work at the university, this was our first piece of kit to take it out of the labs and start making our first K-bricks for development. This is a hydraulic press. You would load the material into the hopper that you see above there, and then the bricks are pressed onto steel plates and this moves through. A great bit of kit to start the concept, start the idea, but really then we wanted to move to a commercial scale.
But this brick avoids the enormous environmental and energy cost that comes with traditional masonry products.
This is like a traditional extruded brick, but we wanted to mimic how people see and use a traditional brick, but with obviously our new innovation and our reuse. Traditional clay-fired bricks, you're mining raw clay from the earth, there's an environmental impact there, but then also you're having to cook them, anything from kind of 1100 degrees to 1400 degrees, huge fossil fuel use, huge energy requirements. These materials have been used for hundreds of years, but we need to find replacements that are more sustainable, and this is just one option that we want to bring to market and help with that.
The construction industry is facing a crisis in the United Kingdom. Bricks are in huge demand. The UK alone imports 38,000 tonnes every year. Meanwhile, there is more demand than ever for building new homes to meet a growing population. But importing traditionally made bricks comes at a huge environmental expense.
So this is one of our key components, and this is a recycled aggregate that we get from a recycling company. This looks, acts, and is like a sand, but this is all recycled old bricks, old rubble, old stone from the construction industry. Amazing. And excavation. We have a smaller sizing here, and then we also have a slightly larger, same recycled aggregates, but what's great about this is you can see the history in here. This is old bricks, old rubble, old stone, old glass. It just tells the story about what this product is. You know, it looks like a brick, but it is not just a brick.
The work to make these amazing bricks doesn't start here. Kenoteq have partnered with a recycling company near Edinburgh, where old building materials are repurposed at this huge site, saving almost 100% of what comes to them from ending up in landfill.
Construction waste, along with commercial and industrial waste, people don't really think about that when they hear the term waste. They think of their black bin bag waste. Construction industry consumes over 50% of all natural resources consumed by the economy as a whole. A waste arisings problem, and with all that natural resource consumption and waste generation, high emissions.
More than a third of waste in global landfill is estimated to come from demolition and construction.
So we bring soil, waste soil and rubble from the construction industry via our fleet of tippers. We put that through a washing plant, which I'm standing in front of. Every town of a certain size will have one of these wash plants in the future. They're really the replacement for your local quarry and your local landfill. That infrastructure will be replaced by one of these plants.
After it's washed, separated and crushed, the different materials are routinely tested for quality before being sold back into the building industry for materials. Almost nothing is sent to landfill. What's more, they're using some of the waste to transform the local area.
So how much waste are you saving from going to landfill?
So this is nearly a 99% circular process. The only waste that goes to landfill is the trash element. So some plastics, polystyrenes, things that are floated out of the system. There's another 25% that I would consider a byproduct, so that's the silt and the clay that we actually use on site to regenerate the wider site on which the plant sits. And then the remainder of the material, roughly about 75%, goes back into the industry off-site.
So you're also regenerating the local area?
This site is an oil shale bing, or waste heap, effectively. So using the impermeable properties of the silt and the clay to cap that material off, stop rainwater infiltrating through any of the sort of hydrocarbon residues that have been left behind, and instead shedding off the sides of the waste heap. And that improves the local groundwater quality. Eventually, when we've finished these sites, there'll be just passive green spaces for the local communities to use. So there's a social impact there as well.
Innovators hope the brick made from this recycled material will revolutionise the industry.
So this is like baking a cake. We take our necessary ingredients, aggregates being one. We also have a recycled gypsum from waste plasterboard that we screen here on site. Then we add those materials to our secret sauce and the recycled pigment that we want, and we take it through to the mixing and batching system that I'll show you next.
By secret sauce, Sam means the binding agent they have developed. They won't share the recipe for that with us, because it's commercially sensitive.
So up here, this is really the engine room of our whole process. Once we've taken the individual elements, this adds the recipe to get the desired mix that we want. So this is the mixer that then feeds the rest of the process and ready to press a brick.
By reducing the reliance on natural resources that won't last forever, Kenoteq are also preventing millions of tonnes of building waste ending up in landfill. But it's not just what goes into this brick that makes it so special. Traditional brick making is a major source of air pollution across the world. And that's because traditional bricks require high temperatures powered by fossil fuels. Kilns release over 1,000 million tonnes of carbon dioxide emissions into the atmosphere every year, which is 2.7% of the total global emissions.
So where's this going now?
So now the recipe that we wanted is made. This is then conveyed across the system here and into our 2 hydraulic presses, ready to be made into the K-brick.
How quickly can you make these bricks?
So really from receiving the input materials through to finished product, it's about a 24-hour process. Compare that with traditional clay bricks that may be over a week, or cement-based products that are at least 4 weeks. This is drastically improved in terms of the time frames.
So that's a really quick time frame. Does that help keep costs down?
Yes, absolutely, and it just also means that we can manufacture and make these products much quicker than those traditional products, get them out to market quicker and have that inevitable sustainable gain quicker.
So normal bricks don't get compressed like this?
No, so traditional bricks tend to be extruded. There's a bit of pressure, but we apply a wholly different sort of magnitude of pressure to form our product prior to our final chemical stage, which is the curing process.
And presumably that keeps your fossil fuel consumption down?
That's correct, Joe. So combined with using recycled materials and also in our pressing and then low temperature curing, that is really how we create the benefits and the sustainability credentials that the K-brick has today.
Their specially patented method for compressing then curing the bricks at low temperatures without the need for high temperatures drastically reduces their carbon footprint without compromising their strength and durability.
Because of the development, because of the lack of the high energy requirements which the cement industry has, and for the high kiln temperatures that the clay industry has, we can avoid much of that CO2 that's related to those processes in our new novel and innovative process.
You mentioned cement there. That's another part of the industry that's also very damaging to the environment.
If the cement industry was a country, it'd be the third highest emitter on the planet. You know, this is a hugely widely used material, but you know, we must find avenues and other ways of creating products that those traditional cement-based products are. So anything we can do to replace some of those high embodied carbon products, you know, I only see that as a good thing.
As global urban development continues at pace, the need to use sustainable materials and building techniques in our cities increases. And innovation to help the construction industry reduce its impact on the environment is key.